Okay, this will be the lesson for 12.4, which is again going to be a multi-day lesson. So this could apply for multiple days. I think I have a minimum of 2 days, maybe 3 in the schedule for this. But in section 12.4 for Calc 3, we're going to talk about the cross product, which is the other way to multiply vectors together. Okay, so in the last section on dot product, we talked about the fact that there are 2 ways to multiply vectors: the dot product, which produces a scalar number and is sometimes called the scalar product. And then we have this new thing called the cross product, and the result of the cross product of 2 vectors produces another vector. Also important to note that the dot product is defined for pretty much any number of dimensions above 1. So 2D you can do it, 3D, higher dimensions, but the cross product is defined only for 3-dimensional vectors, so only in R3. However, it is extremely useful, and we use it all the time in Calc 3. Okay, so when we multiply 2 vectors to form the cross product, that creates a new vector. And the first thing is, geometrically, it's oriented in a way. The resulting vector is perpendicular to both the original vectors, and it follows the right-hand rule. The idea being that if you had 2 vectors, starting vectors, like vector A in this direction, vector B in this direction, then if you put your pointer finger in the left vector, like A, and then you put your middle finger right angles to that, pointing to the second vector that you're doing the cross product, then your thumb would point in the direction of the cross product vector. That would be at right angles specifically that way, according to the right-hand rule. So there's a specific geometric interpretation. Okay, the mechanism for how it is computed is this. It's defined using what's in this box. If vector A has components x component A1, y component A2, z component A3, and B has components B1, B2, B3, then A cross B is defined as A2 times B3 minus A3 times B2 for the x component. The y component of the resulting vector is A3 times B1 minus A1 times B3, and the z component is A1 times B2 minus A2 times B1. Okay, so specifically that algebraic definition that's the way the cross product is defined. Okay, now the way we actually compute this is that these structures here, they look a lot like the determinant for a 2-dimensional vector or matrix. So if you recall, if you have a matrix that is in the form A, B, C, D, right? And you want to take the determinant of that matrix, this maybe goes quite a ways back when you did determinants, that's equal to this diagonal, A times B, the product, minus this diagonal, B times C, this product, right? And because these happen to be in this form, what you can say is the x component of this vector is like the determinant of the matrix A2, A3, B2, B3. And the same thing, this is the determinant of a 2x2 matrix here, right? So in reality, the way we compute the cross product is the cross product of A cross B is we form a 3x3 determinant where we put the left vector in the middle row and the right vector on the bottom row, and on the top we put the component vectors for A, B, and C, for X, Y, and Z, so I, J, and K, just as reminders, right? And just a reminder that when we compute a 3-dimensional vector, the way we do that is while we're working on the first component, so it'd be this, and temporarily we cross out the row and column, and then we take the determinant of the remaining 4 objects, right? So that means we would have essentially component I, okay, or the x component, is the determinant of A2, A3, B2, B3, which is A2 times B3 minus A3 times B2, okay? And then when we want to do the y component, then we switched to doing the this factor, okay? And so we temporarily cross out its row and column, and then that means we have this little matrix A1, A3, B1, B3, and we take the determinant of that, which would be A1 times B3 minus A3 times B1. However, whenever you do a middle value like this, you have to use that multiplier being -1. So in fact, it's the negative of that determinant that determines that. And that will give us essentially A3 times B1 minus A1 times B3, which is exactly the definition. And then the same thing for the K. When we do this, we take the determinant of this little matrix, submatrix. Okay, so probably best to actually just look at an example and see how we do it. To explain it is actually harder using symbols than to actually do one with a numerical example. So let's take an example. Let's say we have vector A is the vector 1, 1, -3. Vector B is 2, 4, 6, and we want to compute the cross product A cross B. Okay, so we would load up a three-dimensional or 3 by 3 determinant here, ijk. This is positive, negative, positive. And then we'll put the A vector here, 1, 1, -1, and the B vector here, 2, 4, 6. Okay, so what we're going to do is, while we're working on I, we're going to consider this part of the table here. And so we would be taking the determinant of 1, 6, -1, 4. Okay, now the way we do that is we take 1 times 6, and then we subtract -1 times 4. Some teachers I've seen talk about this as like the fish or the fishy, like you do 1 times 6 minus -1 times 4. So if you like that notation, you can do that. But basically, 1 times 6 minus -1 times 4 is going to be positive 10. And so that is the x component of the resulting vector that comes from doing the cross product. Okay, let me erase all that, and then we'll do the same thing again, but this time for the y component. So for the y component, we would take, we would not use this here, so we're using these and these, right? We've crossed off these. We're using that. And so the determinant would be of 1, -1, 2, 6. So that's going to be 1 times 6 times minus -1 times 4, 1 times 6 minus -1 times, times 2, -1 times 2, which turns out to be, and then that's 8. But because we're in this second column here, we have to negate that. So we get -8 as the final result for the y component. And then you would do the same thing for the z component. You would say, okay, while I'm working on the z component, I'm going to be crossing off this row and this column. So I've got the determinant of what's left here. So it would be 1 times 4 minus 1 times 2, which turns out to be 2, and that's the z component. So that's all there is to it. It's not as bad as it seems. Once you do a few of them, you'll realize it's not really very bad at all. Although it's hard to explain visually like this. Okay, so the result is, if we had a vector, I'm going to try to sketch it here. If we had a vector A that went, just arbitrary starting here, let's say we went 1 in the x direction, 1 in the y direction, and then -1 in the z direction. So this is kind of pointing down. That's the A vector. And then the B vector is we went 2 in the x direction, 4 in the y direction, 6 in the z direction. So that was pointing kind of up and to the right like this. Then that means A cross B, if you take the right-hand rule, A cross B is going to result your thumb pointing in this direction, right? So the resulting A cross B vector, the resultant vector, is actually 10 in the x direction, 8 in the negative y direction, and then 2 in the z direction. So in fact, it does point in approximately that direction. Right? So A cross B produces a new vector, which is at right angles to the original according to the right-hand rule. So that's the mechanics of how to compute them. Okay, and we'll definitely get a lot of practice on that in homework. Okay, we should talk about physical interpretation. We know that the physical interpretation of dot product has to do with projections. It's about the idea that one vector could project its amount in a particular direction by taking the dot product with the unit vector in that direction. So if we have two vectors A cross B, it turns out, and there's a proof again in the textbook, that if you take the magnitude of this A cross B vector, so you computed your vector like we did on the last page, but then you take the magnitude of it. So you take the square root of the sum of the squares of these numbers, that will produce a number, right? And that number has a meaning, okay? It turns out that you can show that the magnitude of the cross product of two vectors is equal to the magnitude of the first vector times the magnitude of the second vector, but times the sine of the angle between the two vectors. Remember, the dot product one was the magnitudes times the cosine. So there is some parallelism here between the dot product and the cross product. And what that means is that if you take one vector A, let's say we start with this vector as A, and here is the angle between the two vectors A and B, then we know that if we were to make a right triangle out of that vector using this angle here, let's say we have a right triangle here, then if we take the sine of this angle times the hypotenuse, we get the length of the opposite side. So this side right here would be the magnitude of A times the sine of B, okay? So that's like the height of the parallelogram that's formed if you extend the, if you make a parallelogram out of the A and the B vectors. Like if you draw another side parallel to B and another side parallel to A, right? The perpendicular, so if you think of, say, vector B as the base of this parallelogram, then magnitude of A times sine of theta would be the height. And therefore, if I take this times the base, that gives me the area of this parallelogram. So in fact, it's the area of this parallelogram. So one way to interpret the physical meaning of the cross product, not the cross product itself, but if you take the magnitude of the cross product, that actually can be shown to be equal to the area of the parallelogram formed by the two vectors in three-dimensional space. Okay? And the fact that that's true leads to some other interesting conclusions. We know that if you had two parallel vectors, if A and B happen to be parallel to each other and you align their initial points, then the parallelogram that would be formed would have zero area. And that means that the magnitude of the cross product would have to be zero. But the only way that can be true is if the cross product itself produces a zero vector. So in fact, we can use the cross product as a test to determine if vectors are parallel. If we take the cross product and we get a vector whose magnitude is zero, then that means that the two original vectors were parallel to each other, okay? And if we, just as a recollection, if we take the dot product of two vectors and that's zero, that's how we can tell the vectors are perpendicular. So the dot product can be used to test if vectors are perpendicular, and the cross product can be used to test if two vectors are parallel to each other. Okay, there's a related concept called the scalar triple product. Okay, so if we had two vectors, that forms a parallelogram. If we then had a third vector with the same initial corner, that would extend, if you made parallel sides to all of those vectors, it would make a three-dimensional shape, which is referred to as a parallel pipehead. Okay, and it turns out that if you take the cross product of two of the vectors, and then you take that resulting vector and you take the dot product with the third vector, then the magnitude of that ends up being the volume of this parallel pipehead. Okay, so this is referred to as the scalar triple product. Three, because there are three vectors involved, and scalar because one of the things we do is a dot product instead of a cross product. Okay, so the magnitude of what's called the scalar triple product gives the volume of the parallel pipehead. Right? And what that means is that if you want to determine whether or not three vectors all lie in the same plane, so if these vectors all lie in the same plane, let's say we had some sort of a plane in three-dimensional space, and all three of these vectors were lying in the same plane, then this parallel pipehead would have zero volume, right? Because there's no height to it. And so it turns out that if this turns out to be zero, it means that all three of these vectors are what we call coplanar. They were all in the same plane. So that can be a test to determine if three vectors are in the same plane. Okay? And then to make things even more complicated, you can have what's called the vector triple product, which means you take three vectors and then you take the cross product of all three. So you take two of them, take the cross product, and then you take the resulting vector and you take the cross product with the first one. So this one has a really unusual interpretation that's hard to visualize. And I think when I first produced the notes here, I might have had this a little bit too high. So move your A vector a little down here. So I'm going to try to explain it. And basically it's this. If you take B cross C, then you will get a vector that is perpendicular to those two vectors, right? This B cross C vector, the cross product produces this. And then if you take A cross that vector, you'll get a vector that is this red vector that's perpendicular to both of those two vectors, right? So this red vector is perpendicular to the plane containing these two vectors, okay? And what will be true is that this red vector will be in the plane of B cross C, but it'll also be oriented in a way where it is also perpendicular to A, right? So it's kind of like if you need to have a vector in the BC plane that happens to be perpendicular to the A one, then you can take the cross product of the plane you want it to end up in, and then cross that with the A vector to get this other vector over here, right? Very, very unusual situation here, okay? That's used much less frequently. In fact, both these triple products we don't use very frequently in Calc 3, hardly at all. The main thing we're going to do that we want to focus on is how to compute this part, how to compute a cross product. All right. Okay, so the cross product has properties as well. For example, if you reverse the two vectors, then you get the negative. The vector is the same, except it's in 180 degrees out of the way. And that makes sense if you think about the right-hand rule. If I take A cross B, my thumb is pointing in one direction. But if I did B cross A, it would be pointing in exactly the reverse direction. So one is in the negative direction of the other one. Okay, you can also do distribution with a scalar, like you can take C cross A, or you can take C times A, scalar C, and then cross that with B. Or you can first do the cross product and then multiply in the C. Or you can move the C over here, but the A and the B always have to stay in the same order, because if you ever reverse the vectors, then you'll get the negative direction. Okay, and you can also do A cross B plus C, and then the A can essentially distribute in here. So you can do A cross B and A cross C separately and then add the result. And the same thing can happen on this side. You can distribute this in here, but at no point does any A, B, or C ever reverse direction. So if the A is over here and the C is over here, then the A is still over here and the C is on the right when you do that. Same thing, you can do dot products and mixtures with cross products, and you can do them in different orders. Like, surprisingly, you can take B cross C first and then do A dot that, or you can actually switch this and say A cross B and then take the dot product with C, as long as the order stays the same. And the same thing here, this is very unusual, but you can take the vector triple product, A cross B cross C, right? It actually turns out to be equal to A dot C times B and then A dot B times C, but you subtract the two. Very unusual. I've never seen this used in Calc 3, so I don't think you have to worry about this too much. The main thing is, I just want you to just be careful, okay? Whenever you're dealing with cross products, we need to be careful, okay? Because even something as simple as just reversing the direction introduces a change in the direction, right? So I would just say always do cross products, by hand, following the original statement. Unlike the other things which kind of are intuitive, cross products don't behave in intuitive ways. Okay, the last thing we're going to talk about is a physics application of cross product, which is torque. Remember we said that the physics application for dot product was work, because we wanted the percentage of a force that was in the direction of motion. And so dot product gave us that. So torque is an application where it's nice to use the cross product. So in physics, when a force is applied with a lever arm, such that it causes rotation about a central point, then the force times the lever arm distance is called torque. Okay, and so you can kind of think of it this way. If you had let me use green here. If you have a force like this, and it's being applied to something that is able to rotate, and the distance here away from the axis of rotation is called the lever arm, then that's going to cause this to rotate, right? And the farther away this force is applied, the more rotation you're going to get for the same amount of force, right? Bigger lever arm causes more rotation. So the product of the lever arm times the force that's perpendicular to the direction there is called torque, okay? The symbol for torque is tau. This is a Greek letter tau, and it is actually defined formally in physics as a vector. So the torque vector is defined as the position vector for the lever arm, and then cross the force vector, okay? And what that says is that even if the force vector is not perpendicular, by doing the cross product, we're going to get effectively the sine of that, which will give us just the component which is at right angles to the lever arm and actually causes rotation, right? The portion of F which is along the axis will not cause rotation. So by using the cross product, we automatically get just the part that's at right angles, okay? And then because torque is a cross product, it actually is a vector, and it turns out that it is a vector that is parallel to the axis of rotation, according to the right-hand rule again, okay? Right, so we'll see some problems in homework like that where we calculate torque, okay? In fact, let's take a look at one example right now. Let's say that we had this structure. We had two beams that were welded together that were 4 feet long, and they're pinned in some way so that they're able to rotate, but only around this point P. And then we apply a force of 36 pounds specifically in this direction, 30 degrees below the horizontal, where this starts out with the top beam horizontal. So this is going to cause this to potentially rotate in this direction with some torque, okay? And we want to figure out how much torque this 36-pound force applies to this whole object. All right, so remember we said the torque is equal to the r vector cross the force vector. So we're going to need, or we can also say, sometimes in fact this is easier to calculate. For a cross product, we know that that's the magnitude of one vector times the magnitude of the other vector times the sine of the angle. And for torque problems, a lot of times it's easier to use the second formulation. So that's what we're going to do here. So first of all, we wanted to figure out what is the r vector. Well, the r vector is the position vector for where the force is applied relative to the point of rotation. So if we're rotating around this point and the force is applied here, then this r is the position vector for that, okay? Right, so it would be there. And since this is 4 and this is 4, you can do a little Pythagorean theorem to find that this length is the square root of 32. And because this is a 45-degree angle, and this is a 45-degree angle to the horizontal, and this is 30 degrees, and we know that this straight angle has to be 180 degrees, you can use a little geometry to say 180 minus the 70, that should be 75, that's a typo, minus 75 gives me 105 degrees angle between where the force vector is being applied and the rotation vector. If you imagined it being rotated up here to be at the point of application, this angle here would be the angle between the force vector and the lever arm r vector, position vector. So that's 105 degrees, all right? And then we know that the magnitude of the force vector is 36 pounds, okay? So basically I have two vectors here. I have a vector that is the square root of 32 long for the force arm, the lever arm, and then I have a magnitude of 36 vector for the force, and they're separated by an angle of 105 degrees. So then to compute the equivalent of the cross product, then the magnitude of that we know is equal to the magnitude of r, which is square root of 32, times the magnitude of the force vector, which is 36, times the sine of the 105 degrees. And if you plug that into your calculator, you get 196.7. And just like with work, the torque is feet times pounds. So foot-pounds or pound-foot. Sometimes it's reversed for torque, pound-feet. All right, so that's an application for torque, just to show how it works. As far as computation, kind of conceptually, you know, we know that Newton's laws of motion give us this equation for how forces create linear motion, right? We know that force is equal to mass times acceleration. So you can kind of think of in that if you're applying a force, then the mass is basically a proportionality content to say how much acceleration, how much change in speed happens because of the force we applied. You can think of mass as the aspect of an object which resists changing the force, resists the change that the force is applying. So if you have a large mass, then you're going to get a smaller amount of linear acceleration for a given force. If you have a small mass, then you get a lot of acceleration, right? And so there's a corresponding equation for rotational motion, right? Instead of linear acceleration A, we can define something called rotational acceleration alpha, which is how fast the rotational speed is changing, okay? And then the force corresponds to the torque. And then therefore there's going to be some sort of aspect of the object that's rotating that's going to resist that force causing it to rotate, right? So if that thing is large, then you'll get a small amount of rotation for a certain amount of torque. But if that thing is small, you'll get a large amount of rotation. It'll spin very quickly, right? So the thing that corresponds to mass, except for rotation, is called moment of inertia. And moment of inertia is usually in physics books given a capital I for inertia. So it's kind of like rotational mass. So it turns out that like if you have a solid disk like this, that has a certain moment of inertia. But if you had the same mass and it was all concentrated in a ring around the outside, that would have a higher moment of inertia. And it's actually higher, it's harder to cause a thin disk of mass to get spinning than it is to have like a solid disk, because this has a lower moment of inertia. So this will spin more easily than if that same amount of mass was concentrated here. Like if you had an aluminum disk here and you had the same mass, but it was like lead all in a thin ring around here, it would be much harder to make the thin ring of lead spin than the thicker disk of aluminum. Okay. Yeah, so just a little connection to physics, but the main thing that we need to get out of this chapter as far as for Calc 3 is the method of computing the cross product, to be able to compute this cross product. So understanding how this works, like understanding this example, is the most important thing. Okay, and that's where we wrap up this. You can go ahead and try the homework from the various sections of 12.4 at this point.